All right, so continuing with chapter 8, we've finished talking about Earth's interior and its magnetic field, including how that magnetic field helps protect the atmosphere. So now we're going to get into more details about the composition of the atmosphere and about how it can change from certain influences. Um, there's, obviously lots of different ways the atmosphere can change, lots of ways that we can hold on to our atmosphere, as I talked about, right, with the magnetic field, the perils of losing an atmosphere if you don't have a magnetic field, and so on. And the context we'll kind of put that whole discussion in, which is a really nice way to think about it, is all going to be about an energy balance. So I hopefully that will make it all more clear. But before we get to the concept of the energy balance, let's just cover some details about the atmosphere. So in the very beginning, which is kind of a funny statement. So when the solar system began, it was all hydrogen and helium. At least, that there were heavier elements, to begin with from previous generations of stars. That's where all heavy elements come from, which of course some we'll talk about later. But the leftover gases that would have coalesced and been gravitationally attracted to the planetismals and the eventually early planets that formed from the amalgamation of said planetismals would have been all hydrogen and helium, because that would have been the predominant available gas in that early disk that was the primordial solar system. There would have been at some point, well, when the Earth was still, molten, still differentiating, an atmosphere entirely of hydrogen and helium. However, as the sun began to become a proper sun and fusion began, and the solar wind started streaming out into the solar system, as well as just the heat associated with the photons and the light streaming out into the solar system, both from the sun, we would have lost that early primary atmosphere. Okay. And we don't have really any of it left today. But to understand why that is, I have a question for you. Okay. And by the way, I think this statement is a good thing to note here. It says that formed from the gases in the stellar nebula. So just remember that this primary atmosphere just matches the stellar nebula itself. It's just, what were the gases available? But do hydrogen and helium have large or small masses compared to other elements? Think periodic table. Let's see. So, yep. So they have, yep. Small. Nice. Okay. They absolutely do. They have the low numbers on the periodic table. They have really small atomic masses, is the way we describe it. So they have the smallest mass. Okay. Oops. And that they're not I mean, helium isn't the second smallest, right? Um, it's well, okay, actually, helium. No, helium is. Yeah, sorry, because helium has the two protons. Next, it's just going further along, then we have our other heavier elements. But helium is the second lightest element with just two protons. All right, and hydrogen just has one proton, helium has two. The masses here are interesting because notice that hydrogen is listed as H2. That's because when you have hydrogen, almost under any conditions, it forms what's called molecular hydrogen. And that is two hydrogen atoms together. They form a very stable bond and they form what's called a diatomic molecule. And so when we talk about hydrogen gas, it's almost never going to be atomic hydrogen. So instead, it's this molecule, H2. Two individual hydrogen atoms, each with a nucleus that just has a proton and no neutron, hence the mass of two, because there would be two atomic masses because of the two protons coming from one hydrogen each. Electrons don't count in the mass calculation because they are over 1,000 times lighter. So they just don't contribute to mass, not significantly. Helium is going to be atomic. It's an atomic gas, so it's just by itself. Each helium particle in the gas is just one atom, and it has an atomic mass of 4 because it's got 2 protons and 2 neutrons inside that one atom's nucleus. That's where the numbers come from. But I said it all got lost in the space, that primary atmosphere that matched the stellar nebula, because of the lightness. The question about the light nature of these elements was not just random. It was asked because it helps explain why we don't have this primary atmosphere anymore. It is just too easy to energize and too easy for those energetic, very light particles to pick up enough speed to just escape into space. In the same way that we launch a rocket and that rocket it achieves escape velocity, which is fast enough to to leave the gravitational pull of Earth, and go off into the solar system or whatever destination. Well, that idea applies to molecules as well, and it just takes a lot less energy to have something so small achieve a great velocity. So it's rather easy for hydrogen and helium in particular, the lightest things out there, to achieve escape velocity. So they don't get retained in atmospheres under most conditions. They just escape into space. And they would only have really got gravitationally pulled into the atmosphere in the first place because there's probably so much excess hydrogen and helium in that early nebula before it had, just kind of been cleared out of the way by the solar wind, or just, gradually gravitationally attracted to whatever had a great enough force to hold on to it. What is interesting is that we will return to this whole discussion of hydrogen and helium when we get to the gas giants. So, because if you're thinking like, okay, well, sure, it escaped into space, but where does it go after that? If it doesn't, get pulled into the sun, well, that's where the gas giants come in. And there's obviously something going on there because they seem to actually have a lot of hydrogen and helium, right? So, hint, it has to do with their large size. But then how they get large in the first place, what came first, the chicken or the egg? In this case, unlike with the chicken and egg, there's an answer. All right, but key idea: the very light atoms move very quickly. Just that's it. It just takes not a lot of energy to accelerate them. Right? They can easily escape gravity's pull. And we'll actually see the equations for this in the slides when we talk about Mercury. And I'm going to go really quickly through those because there's a homework assignment that covers it as well. So it's going to be like, okay, here's your introduction to it, and you'll get to practice with the homework. And what I mean by that is calculating escape velocity. So now we finish our discussion of that primary atmosphere, which didn't last long on Earth. Okay. By the way, that's why Earth is shown like this. This doesn't look a lot like Earth. That's because this represents that molten early Earth. All right. So now we have Earth essentially before life. So this is the probably the first billion years or so, first 500 million years, before any life had evolved, or during the very beginning of your single cell life starting to take hold on Earth. Okay, and that is the secondary atmosphere. And the secondary atmosphere was composed of water, over half water, carbon dioxide, sulfur dioxide, nitrogen, and noble gases. The reason that these molecules and atoms got into the atmosphere was mostly from outgassing. So instead of being captured from the solar nebula, they were being created by the cooling planet. The now differentiated planet with its solid crust started to fart things into its atmosphere, I guess, right? As a crude way to describe it. It essentially, it's cooling, and the volcanoes are erupting, and that's the source of gas. Also, all the liquid water, due to our location in the solar system, our distance from the sun, and the fact that we can have liquid water, well, that liquid water would have been in a state where a lot of it was, you know, only liquid for a short period of time, and instead, you know, quickly evaporating and existing in that water vapor stage, right? That's why so much of the atmosphere was water, because it was a hotter planet, and it was a planet where water was not easily staying in the liquid phase. Instead, it was becoming a gas very readily. All right. And these are just, kind of examples. There's a lot, phases within phases of the secondary atmosphere, but this is kind of a generalization of the early atmosphere of Earth. Okay. After that, shortly lived primary atmosphere. All right. Anything else I want to say about it? Right. So, you can see the the sulfur dioxide. Let's see. No, that's the nitrogen. Sulfur dioxide isn't shown. We just see the water and the carbon dioxide, and then the NH3 is always. My chemistry is not the best. Methane, perhaps, but it's most likely the source of the nitrogen that, because there might have been a splitting up of this molecule. Sulfur dioxide would have been outgassed by volcanoes as well. Okay. All right. Now, current atmosphere. We're going to explain where it comes from, but first let's just show its difference. The current atmosphere, this is the atmosphere that you're breathing right now, is really different from, obviously, from the primary one, and also really different from the secondary atmosphere, which I said predated life. So kind of stands to reason maybe this atmosphere didn't support life. And you can actually, probably notice right away that this secondary atmosphere wouldn't support, at least not us, because there's no oxygen here, right? Plants actually seem like they do okay, right? Carbon dioxide, right? Because we know plants breathe in carbon dioxide. But here we go. The atmosphere that does support, oxygen dependent life has oxygen in it, only 21%, right? And that's actually an interesting thing that a lot of people don't realize. If you go, ask someone on the street, like what's the most common molecule in the atmosphere? I guarantee most people aren't going to say, or element, nitrogen. All right. Although actually, the nitrogen does exist as a diatomic molecule. Remember how I said, hydrogen naturally becomes diatomic? So does nitrogen, and so does oxygen. So when we talk about free oxygen, the oxygen we breathe is all O2. That's diatomic oxygen. And the nitrogen that is, so predominant in our atmosphere and composes 78% of the mass of the atmosphere, and that's what, these percentages represent. Well, it's going to be N2, so two nitrogen atoms together. Notice there's O3. Well, that's also oxygen. So both the O3 and the O2 together contribute to the 21% proportion here. But the O3, we don't call it oxygen, we call it ozone. It's the ozone. It's not the kind we breathe. We can't, survive off of ozone. But it is oxygen, and it could be split into breathable oxygen pretty easily. But it's not on its own. Noble gases make up 1%. They were there, by the way, right? I didn't mention them. They're the xenon and neon. So these noble gases, part of the reason you're going to find them in atmospheres is their very noble nature. They don't tend to make molecules, so they just kind of exist around unless they escape somewhere. And they're not going to get easily trapped because, after all, they exist in a gaseous state at the temperature, of the surface. So they can't, phase change. Carbon dioxide is very low, right? Less than 1%, about half of 1%. So it's a tiny value when we talk about the carbon dioxide in the atmosphere, right? It gets talked about a lot, right? The carbon dioxide amount is going up, and it's, directly related with climate change. And, it's a hot topic, right? Rightfully so. But the actual value is dramatically low. So so consider that, and we'll talk about why it is so low. Water is not a big part of our atmosphere. because the vast majority of water stays in the liquid phase, so water turning into a gas is obviously happens. We have our whole water cycle. We got, rain and clouds and mist and fog, but that's an overall tiny percentage of the available water on Earth. And sulfur dioxide, which was a big component in the secondary atmosphere at 13%, now is less than 1,000th of 1%. It's actually 1/10,000th of 1%. So how did we get here? How did the secondary atmosphere become the current atmosphere? Well, what do you think happened to the water in Earth's atmosphere? Thank you, Alexander. It's ammonia, not methane. That's it. I know it's always one of the two. And I was like, oh, should I say ammonia? No, it's probably the other one. Somehow I gotta find a way to remember that. I'll look up a suggestion online. Like what's the mnemonic to remember? But anyway, current question. What happened to the water in Earth's atmosphere? What do you think? All right. Seems reasonable, right? It condensed, right? Evaporated into the air wouldn't, it'd still be there, right? Because after all, we're all talking about a gas. Okay. Floated off into space, maybe, but unlike the hydrogen and helium, it's kind of heavy. So, so turns out it did condense to a liquid, right? The planet cooled and allowed for the condensation. All right. There's the oceans. Okay. So there would have been bodies of water back, in that primary, but not nearly as much as today. And as we know, those oceans help drive plate tectonics. So it ended up being a key aspect of the world we know today, that the fact that water condensed to a liquid. It also froze. We have poles, right? But not the majority. 1% of all water is frozen into the poles. So, significant, but still the best answer would have been condensed to a liquid. All right. So there we go. There's our answer about the first change. The 58% water that made up the secondary atmosphere became, less than half of 1% because of condensation. All right. But where did the CO2 go? Because the CO2 was 23%. It was the second most common component of the atmosphere. Where is it today? And, you know, in contrast, if you look at the Martian atmosphere, which is very thin, it's primarily CO2. If you look at the Venusian atmosphere, which is incredibly thick, so Venus has this crazy thick atmosphere over 100 times thicker than ours, which keeps the planet just boiling hot at the surface. Well, it's also primarily CO2. So literally the two very different planets of Mars and Venus have mostly CO2 atmospheres. So it seems like CO2 is actually a pretty easy thing to hold on to. It sort of seems to be the gas that a gravitational body, a big mass can hold on to easily at this distance from the sun. Kind of the range of distances that the three terrestrial planets, Venus, Earth, and Mars, are at. So what I mean is it's kind of the default of what gas you're going to end up with. But we don't have it, right? Where did it all go? And we started with plenty of it. Well, here's your answer. Okay. So some of the CO2 was absorbed by water. Okay. So this is deposition in earth, in stone as well. All right. So you have these non-biological processes where CO2 can get absorbed by liquid water. And then when water interacts with certain minerals, then it can get deposited in stone. But a more important factor, or at least, yeah, I mean, I think so. Actually, I have to check if it makes up the majority. But either equally important or more important is how CO2 can get locked into plants. But why locked, right? Because consider a plant. Here we go, right? The tree So at some point, life evolved on Earth that absorbed CO2, used CO2 as a energy source for those chemical processes of the early life. And it's that whole interesting idea, the primordial soup, right? That you have some self-replicating molecule, and it ended up being that CO2, since it was abundant, was, a natural input. And you could take that CO2 in, you could break that CO2 apart, release its stored energy in the molecular bonds, and have essentially a food source, so to speak, which would be an energy source. All right, that's your nutrient source, coming via CO2. And then the chemical processes that allowed for that had a byproduct of O2. Okay. Well, what happened with a lot of plants is that they then absorbed the CO2 and then trapped it underground when they died, along with the animals that ate the plants. So when we talk about fossil fuels, that's what we're talking about. And there's even some cool ideas about this because there's been some key points in Earth's history, right? Because life's been around for over 3 billion years of the 4.5 billion years the planet's been around. And we have a lot of kind of evidence that there's really really early life that went back to surprisingly early in Earth's history. But some point, kind of early plants came along, and there were hundreds of millions of years in their early, kind of evolutionary history of Earth where there were plants, but nothing to decompose plants. If you think of, decomposers, obviously, herbivores that eat the plants and then digest it, and then, have some sort of, like cows pooping out their cow patties, right? That's a form of decomposition, right? But another really crucial one is what fungi do, right? So fungi, eating wood and turning it into the mush. Well, that the whole kind of like kingdom of life, which is fungi, weren't around for a long period of time that plants were. And so a lot of our fossil fuels, a lot of the carbon dioxide that's locked into minerals comes from epochs where there were lots of plants but nothing to decompose them. And so they got compressed down and turned into big stores of CO2, but that not really like cycled around in the way that they would be today. So I guess my main point, to not just completely go off on a tangent, is that there are key stages in Earth's history where CO2 is getting locked into the ground at a much greater rate than it is today. So like we're not building up, the fossil fuels, just the natural ecosystem that exists on Earth today aren't building up fossil fuels at anywhere near the same rate that like that if a future civilization could find, say, 100 million years from now, because just life has changed significantly. So it's kind of we're seeing these past phases when we dig down and find them. But point being is that both the dead animal and whether you know its remains, its fossils, whatever. And a lot of the fossil fuels come from like really small sea-based animals. So whole, areas of small crustaceans existing in, profusion within the Earth's oceans, and then, and them dying, getting, sedimented on the bottom of the ocean, and then layered and layered up, and then becoming the big reserves that we know today as, oil reserves. Well, those were all once little crabs and shrimp and, ancestors of oysters and clams and so on that, died and got compressed and then just became the oily substance down between sheets of rock that, again, that we call oil. Um, this interestingly too, just I have to point this out that, this O2 byproduct from plants was just that, right? Available CO2, self-replicating molecule, if that's where life came from, you know, um, took advantage of it, started absorbing it, and then essentially, using oxygen as the waste product of that metabolic, life form. Well, then what are animals, right? Animals were just a an evolutionary step where some, some random mutation led to a different small, single cellular or just a few multicellular basic organism that was able to take advantage of the byproduct of everything else. So that's all, all the oxygen breathing animals on Earth are just that, this legacy of being like, hey, we can use this thing that plants just reject. And it's kind of neat to think of it that way. So, but there is where the carbon dioxide went. The carbon dioxide was absorbed through biological processes and also non-biological processes, mineral-based ones. And it then got removed from the atmosphere and instead, just mostly locked up underground. Now, it still remained necessary for all those plants. So there had to always be a certain amount of cycling, but the plant populations would have, existed at the limit of how much was being cycled. And so, the amount of plants that the earth can support is limited by the amount of CO2 that is being released rather than, just locked up because it doesn't, not all of this is going to remain locked forever. Even if it wasn't for humans, pumping up this, all these dead animals and burning them and therefore releasing the CO2, what there'd be, just other ways that the CO2 would get released. Okay. And the sulfur dioxide got absorbed by the water and then deposited in stone. So a entirely mineral-based process that is facilitated by liquid water explains the sulfur dioxide disappearing from the atmosphere. Okay, so there we go. Right, locked up in sediments. Sediments then can get, pulled by plate tectonics in different places. Okay, so we have absorption of the sulfur dioxide. That's why it went from 13% to just completely gone. Because essentially, just think liquid water was really good at absorbing sulfur dioxide. It didn't stand a chance. The nitrogen just survived. So the nitrogen was just there in the first place, wasn't involved in any absorption or biological process, and it just stuck around as useless as ever, you know? So it's kind of this, just kind of always just been along for the ride. And so this actually does imply an interesting aspect here that the secondary atmosphere was way denser than the current atmosphere because in order for 5% of something to now represent 78%, well, that means the total has to be smaller. So the total amount of mass within the atmosphere has gone way down. But that kind of makes sense because obviously it's a cooler Earth, one that can facilitate liquid water. But it is a much, much less dense atmosphere today. This secondary atmosphere would not been completely comparable to the current Venus atmosphere, but kind of more similar to it in terms of having a bunch of water in the atmosphere and so on. Although actually, Venus has actually lost its water in its atmosphere for different reasons. But we'll talk about that next week when we talk about Venus. All right, and then finally, the noble gases, just like nitrogen, just survived. Okay, and if you're obviously some of them must have been reintroduced in order for that 1% to stay 1% proportionally. Um, so I guess there's a continuing probably outgassing of noble gases. There's big reserves of helium, for example, under the ground, and so there's been that gradual rate of slow but gradual rate of outgassing of noble gases has allowed the amount to creep up, but the proportion to stay the same. Okay, but that explains where everything went, whether it survived, condensed, or absorbed. But it leaves one unanswered question. But of course, we already know most of the answer, and that's the oxygen, because this is just brand new, right? This wasn't involved in the secondary atmosphere at all. So where did the new component come from? Right? It came from photosynthesis, because photosynthesis releases oxygen into the atmosphere. That is the metabolic process of plants. Okay, and so plankton and algae in the ocean are the primary drivers of oxygen in the atmosphere. So they're the plants that produce the most oxygen, all right, rather than ground-based plants. But the ground-based plants do add to the overall oxygen output. So it was photosynthesis that led to the free oxygen in the atmosphere. And this is an interesting thing that scientists talk about a lot is that there's no process that other than photosynthesis that is known to produce free oxygen. There's no non-life based process. There's no, just purely mineral or, just purely, just chemical without life that produces free oxygen. So when we see free oxygen in another atmosphere, which we never have, then it would be a good suggestion that there might be some form of life on that world that has free oxygen in its atmosphere. So a lot of observation is focused on looking at exoplanets and trying to carefully analyze their atmospheric compositions to look for exactly that. As not a guarantee by any means, but since we don't know of any other way it's produced, perhaps it would indicate life. And we could somehow confirm it, maybe. Okay. So that's the breakdown of the different stages of the atmosphere and a summary of the current atmosphere and why it's that way. Now, let's get to that energy argument that I mentioned before. Okay. So I want to kind of support the transition here. We're talking about the atmosphere, we still are. And it's just we're going to turn our focus to kind of the energy coming in and out of that atmosphere and how these different molecules can facilitate that energy flow. And one of the biggest tie-ins is going to be the CO2 because carbon dioxide happens to play a big role in potential energy exchange. And exchange with what? Well, with space. Okay. So we want to think about energy coming from space, coming from the sun, right? Sure, there's other sources of energy, but they're insignificant compared to the energy coming from the sun. And then the energy going back out into space because Earth radiates energy back into space. It has to. Okay. But before we get to that, and I'll repeat that statement because it's not one that's immediately obvious. It's actually kind of an interesting idea, but once it becomes clear, it really helps with understanding all of this. Let's define, so before we do that, let's define two words here, weather and climate. Maybe you've heard this comparison made before. Climate is the long-term average of weather. So when we talk about climate change, we're not talking about weather change because weather is just random events. Okay. The weather is just what happens on a particular day or, small period of days. So climate is what you expect. Weather is what you get. This is a quote because it's not, scientifically sound, so to speak, but it does capture the idea, right? So weather is a random event, climate is an average. So when we talk about the global average temperature, that would be a marker of climate. All right. And the weather would be, all this variation. So the up and downs, which is random, but then the trend is the climate. And you can see it here, right? The temperature is trending upwards at a steady rate. Okay, so now back to the energy argument. There's a lot of slides here, but actually we'll go through them quickly because they're almost like made like an animation. So the incoming and outgoing energy are balanced at the equilibrium temperature. So any planet will reach a temperature that facilitates equilibrium. Not because that's the way to do it, but because it'd be a violation of physics if it didn't. Because if the planet wasn't at equilibrium, then it would just be steadily heating up. Well, that's impossible, right? That would be the planet just, absorbing more and more energy. And why would it be doing that? Like what would be the consequence of it? Well, I mean, it'd have to become some sort of molten planet after a while. But how could it, right? How could it just take in more than it's giving out? Instead, it has to reach an equilibrium. And this comes down to the laws of thermodynamics in terms of the kind of the thorough backing of concepts like this. And it's just fundamental to the nature of how energy, entropy, equilibrium, how these ideas work. And they've been, you know, validated in many different aspects of, study. So what I mean by this, so, hopefully make this perfectly clear, is that incoming sunlight is the input. Okay, so you got energy coming in, and then planet heats up to some temperature where it's able to radiate outgoing heat. If we take this back to chapter 5 material, we know that the incoming sunlight is shortwave radiation, right? Visible spectrum, few hundred nanometers. And the outgoing heat is infrared, relatively long wave radiation at a few thousand nanometers. Okay. And that just has to do with black body radiation and the different thermal spectrums that are produced. But the point is that the planet will warm up until it's able to release a total amount of energy exactly equal to the energy it absorbed. And so there'll always be an equal amount of energy coming in and going out. And the way that the equilibrium is achieved is by temperature. So think of temperature as the mechanism to achieve the equilibrium, because the temperature dictates the wavelength. Okay. And if you think of the black body curves, of that type of radiation, that continuous spectrum or black body radiation spectrum, the actual size of the curve, the amplitude of those, kind of lopsided bell curves, they that isn't always the same. And it becomes larger at different wavelengths. So it's not just where the peak is that's dependent on temperature, it's also the size of the peak. And so that means that, the planet's, as it adjusts its temperature, it's adjusting how much energy is flowing back into space. Okay. So that's, in other words, these arrows, you think of them like kind of, they will sum up, they're all smaller, right? But they will sum up collectively the one big yellow arrow. And that has to be the case. And we can call this Earth's energy budget. It has to be as much coming in as going out. And unlike people, they can have a budget that's out of whack, right? They're spending more money than they're making. Well, you know that could go on for a certain period of time, and then the person runs out of money or dies in debt or something. But if the person didn't have a finite lifespan, then eventually they'd have to you know have a point where as much money is coming in as going out, because they couldn't sustain a a lopsided budget forever. And that's the idea of the planet, right? Once you think about planetary timescales. This breaks down some of the processes and different amount, the actual values and percentages. Uh, we'll skip over those details for now. They're quite interesting, but you can look at them on your own. This is just going back to the current atmospheric change and how that is affect how the carbon dioxide level is going up. We mentioned this before. Okay. And that's creates something called the greenhouse effect. What is it? Well, the trapping of infrared radiation. Okay, but we'll see that. So here we go. Earth's energy budget. This is just elaborating on that balance idea. So we have sunlight hitting the Earth. The atmosphere is shown as this kind of, blue ring, not at all the scale. As I mentioned, the atmosphere is only about 100 kilometers thick. The radius of the Earth is 6,000, approximately. So, right, it's tiny. So incoming energy, outgoing energy. Again, incoming as, sunlight and that visible band of energy, outgoing as infrared radiation, because the Earth glows, right? But it glows in the infrared, so we don't see the glow with our eyes, right? So the energy into the Earth has to equal the energy out into space. And again, if that wasn't balanced, the planet would just be either continually cooling or continually heating up. And you still might be thinking, well, yeah, sure, then it I could see that. I could just see it cooling, but not forever, right? Eventually, that cooling or heating will cause some change in the atmosphere and the surface, and that change will lead to a rebalancing. Because Otherwise, the Earth would just change, right? And then the rebalancing would be on a bigger scale, right? If the Earth somehow could just keep absorbing energy until it became so hot that it blew up, well, then the idea of the energy balance would have to be on the scale of the solar system, because now the explosion of the Earth would have to balance out with, the overall energy absorbed by the rest of the planets or something, So there always has to be some energy balance. And being just an isolated spheres floating in the vacuum of space, the energy balance happens on the scale of the Earth. It's not able to, like I said, heat up until it blows up. So, that's why we expect the balance to be contained within Earth. All right. So sunlight hitting Earth, energy flux. Okay. So this is just this kind of the term we're giving to it. Same term we saw when we talked about sunlight during different times of the year. Okay. And then the infrared radiation leaving Earth is driven by temperature. So think of the terms in the parentheses as sort of being the 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 input variable that defines this quantity. So the sunlight hitting Earth is dependent on this concept of energy flux. The infrared radiation leaving Earth is dependent on temperature and the variable temperature. So if Earth absorbs more light from the sun, it gets hotter. What happens to the infrared light the Earth emits? You tell me. So if the Earth heats up, what happens to the infrared light? Less energy emitted as infrared, no change to the light, or more? Okay, so one or three. Okay, three, three. Most people say three. Good. Exactly it. And that's the way infrared light works. You get warmer, you emit more infrared. The more infrared light is emitted. So that's the budget. Okay. So if more, right? So this is the relationship between flux and temperature. If the flux goes up, the temperature goes up to compensate for it. So if the sunlight from the sun suddenly became more intense, therefore the actual flux, which if you remember is just energy per area, if that increased, then the temperature would increase accordingly, so that the amount of well, outgoing flux, but just radiation leaving Earth went up equally to the input. Okay, so if this was our model, if it was as simple as this, it would just be raise one, the other goes up as well. Okay. So, how does the atmosphere get involved? Because so far, this would be great for a planet that didn't have an atmosphere, because then really the only thing that would matter would be the surface, and the surface warms up, the rock, gets a little bit warmer and it just radiates more or less, right? Or if the, sunlight cools, the rock gets cooler and radiates less, right? So, but the balance would just be that. But the atmosphere makes the balance have more to it, more to consider. Okay, which you can kind of see by the extra space, right, included in the equation. So one thing that the energy budget with atmosphere needs to consider is reflected sunlight. Okay, so this is sunlight that gets reflected off of the atmosphere. All right, also can get reflected off of the surface if there's especially reflective regions on the surface, such as snow. All right, and I'm going to skip over. So don't bother to answer this one, but I'm going to tell you. So in winter, white snow reflects more light off the Earth instead of absorbing it. What happens to the infrared light the Earth emits? Okay, less. So if there's more reflection, then infrared light doesn't have to do as much work, because the energy budget now is being partially sustained by the reflection. So you don't need to radiate as much in order to balance the input. And what that would look like in the equation is that we introduced an outgoing amount of energy because of the reflected sunlight. We put it on the left-hand side of the equation, but put a negative on it, okay? Because it happened, before the absorption. So kind of if you think of this as just order of occurrences. And so because of that, right, because if we have this one going up, we don't need as much infrared light getting radiated in order to maintain in order to maintain the budget. That means that the equilibrium temperature doesn't need to be as high. So before I kind of mentioned the temperature as being the thing that changes in order to, keep the balance. But now the temperature was mentioned last. Instead of it being, the cause, now it's the result. And why is that? Well, because by introducing the reflected sunlight, we're now making that like the change to the system. So then we're saying, okay, well, that means that the amount of light that's going to get, you know, emitted into space by heat radiation doesn't need to be as high. Well, if it doesn't need to be as high, that means the temperature must go down. So now the temperature is less because there's more reflection. Okay. And we're going to kind of see that from now on, that the temperature is going to be the variable that gets affected rather than the variable that kind of you have independent control on. So you think of it as the dependent variable of this system. Here's an activity. All right. This mentions, and there's always some nice links down here. This mentions actually the simulation from an excellent website called PhET, where you can look at different greenhouse gases. The greenhouse gases absorb infrared light very well. So they're really good at absorbing light, not reflecting it. Okay, so what would that look like? Okay, so if we have considered the condition that includes reflection, which are kind of these orange arrows, the one we were just talking about, but now also consider greenhouse gases, then we're going to have some amount of absorption or trapped infrared. So the Earth will still do its thing where it wants to, reach a temperature that, maintains that equilibrium, and it's going to emit infrared light, but some of that infrared light is going to get trapped in the atmosphere because of gases like CO2, those greenhouse gases, which even in trace amounts are really effective at trapping light. And the way they do that just comes down to their particular structure and the way they interact with light, essentially the way they vibrate. So now we'll have all four terms in our energy budget, the complete picture. Energy in has to equal energy out. That has never changed. That's always remained true. Okay. So we can call the reflected sunlight the albedo. That just refers to how reflective a planet is. So we talk about surfaces of the planets. We can talk about them having high or low albedo. Same for moons. And then the amount of infrared radiation that's getting trapped in the atmosphere is the greenhouse gas concentration. So just to summarize here, each time we have a term sort of describing the physical phenomenon, and then underneath in parentheses, we have the actual measurable quantity that's related to each. Okay, that's that is the variable that is directly related to the phenomenon. So if more energy in, then the temperature increases, causing more energy lost by emitted infrared radiation. This continues until the energy output grows to equal the input energy. If more energy out, then the temperature would decrease until equilibrium is again reached. Okay, so you can always be in the midst of a readjustment, but that readjustment is always just, on the way to returning to equilibrium. And I mean, the time frame can be long, right? It can be a lot longer than a human lifespan, certainly, but it's still always trending towards equilibrium. Sunlight hitting Earth, right? If you increase that, that's more energy in, which means that if then you account for reflected sunlight, that's a little bit less energy in. If you're radiation out, then that's going to push the other side of the balance up. Your infrared radiation trapped will lower that side of the balance. And so all four of them operate like this. Okay. So on the energy inside, we've got the two opposing effects on the energy out. So if we increase CO2, we are trapping more radiation in the atmosphere. So how, so now we just increase that one arrow. How would we balance the system? Because it becomes unbalanced, and the only way for it to balance is for the infrared light radiated by Earth to increase accordingly. Well, how does it increase? It increases by the temperature going up. So only an increase in temperature can balance a change in CO2 if nothing else has changed. All right. So if your only change of the system is more greenhouse gases, then the only other like variable that is possible of changing, because it's still the same amount, same albedo, right? We don't have any more reflection, and the sun hasn't changed, so the sunlight hitting has to be the same. So the only thing that can change is the infrared light. Therefore, the temperature has to change. So what happens to the temperature of Earth as the albedo increases? So this is just some other cases, just to show that the CO2 case is what we care about when we talk about climate change, but there could be other types of change, just to show that like they all follow the same rule. So I'm just going to quickly go through these. So the temperature would decrease because of more reflection. Okay, what that would look like in the equation version is the reflected sunlight would go up, but if the infrared, so therefore, if the greenhouse gases remain the same, right? So if there's no change in the atmosphere, but just a change in albedo. So somehow we suddenly the Earth just became shinier. There's just a bunch of you know, like people just covered the Earth in solar panels to the point that literally they were like covered whole continents. Well, that would significantly increase the albedo, and that would cause the temperature to go down. So, there actually would be a way of just, if you just made the surface more reflective, you could bring the temperature down without changing the atmosphere. Kind of interesting, right? Not probably a realistic way to adjust for climate change. If you worry about the temperature increases, which there's reason to worry about, but you know, at least a possible idea. Okay, and so this is the idea, right? An unbalancing with albedo. So you introduce an unbalance. How do you account for it? Well, you have to decrease this arrow to rebalance. Okay. And okay, what about another case? What if the sun suddenly became brighter? Well, that would be an unbalance in flux, right? So flux gets bigger. And if the atmosphere didn't change, the only thing that could would be the temperature of Earth, right? And because the temperature can readily change, right? But the atmosphere doesn't necessarily, right? Unless there's something, some process that's forcing it to change, like digging up a bunch of CO2 and burning it, for example, right? So in this case, though, if the sun suddenly became hotter, we have a unbalancing with flux. So we introduce a big arrow. How do we compensate for it? Well, we have to balance the temperature like that. All right. So the idea is that no matter what happens, balance gets achieved eventually. But as you can see, it all comes down to how it gets achieved, what is possible to change, and how to, facilitate that change and understand, what will change automatically and what will not. Hopefully that gives you a good picture about energy balance and climate. All right. And with that, we're going to take our 5-minute break, come back and talk about the moon and Mercury to wrap things up today.